Good. Welcome today to the session Measurement Devices, all about measurement device handling in the printing industry. My name is Tim Hansinger. Before we are going to start, let me just introduce myself quickly. I'm Tim Hansinger. I'm working in the service and consulting department for GMG, so I'm mainly doing installations on site at customers, also trainings on site. I'm with GMG now since 2007, so quite a while. Before I went to GMG, I studied media technology. I specialized in printing technology, and I wrote my diploma thesis at FOCRA in Munich. The agenda for today would be, first I want to talk about measurement device types, about measurement device vendors. So I selected just a few measurement device vendors, and we are going to see their devices. Then we will talk about some general color measurement stuff. So the ISO norm, for example, that describes the general color measurement information. And after that, we will talk about new measurement standards, especially the M1 measurement condition. Then we will talk about reliability and repeatability of measuring devices. Then I will talk about some tips and tricks that we have, how to handle the hardware. And close to the end, we will talk about the XRGA standard from X-Rite, as well as which software to use for measuring. So that will be the plan for today. And now let's start with the measurement device types. So basically, there are a few different measurement device types. So for example, there is a densitometer. A densitometer measures the reflection through a special filter, and it gives you the thickness of your ink layer as a result. So you will get the solid density as an information when you measure using a densitometer. So a densitometer is mainly used in when you are printing on an offset press, for example, you there measure your densitometry. Then there's a spectrophotometer. A spectrophotometer illuminates the surface that you want to measure, and then it measures the complete reflected spectrum of the visible light, also parts of the invisible light. So by measuring this whole spectrum of the light, then you can then we can apply, we can convert this spectral data to, for example, the LAB color standard, and in this standard we can then, for example, calculate differences between two colors that we measured and so on. When we talk about spectrophotometers, then all the parameters that are describing how to measure with a spectrophotometer or how a spectrophotometer should work inside are defined in an ISO standard. That's the ISO standard 13655 in revision 2009. And we will talk about this standard also a little bit later during this session. The densitometer as well as the spectral photometer, there are basically two available possibilities that you can measure with those devices. So you can do reflective measurements with most of the devices. So you are measuring light that's reflected from a surface. And there are also some measurement devices that support a transmissive measurement. So where your light source is shining from behind through the material that you want to measure. So this is for measuring transparent materials, and then your sensor is on the other side and is measuring the spectrum or the density that's passing through there. I also want to talk quickly about two other devices, two other measurement devices. I won't go into much detail about them, but just to make it more complete. So there's also the possibility to use a microscopic image capturing, where the measuring device captures a microscopic image, and then it calculates. So, for example, this is used mainly when you're, for example, measuring a printing plate. So when you have your CTP system and you get out your printing plate, and with such a measuring device, you can check if your 5% point that you want to apply to your plate is really a 5% point, or if maybe more or less is used. So you can use such a device to calibrate your CTP systems, to measure and calibrate them. And then there are also gloss meters. A gloss meter it measures basically the reflection of a surface. So you have a defined beam of light at a fixed intensity and at a fixed angle, and you're projecting this one onto your surface, and at the opposite angle you have your sensor that measures the light beam. So in doing so, we can really you can measure the reflection of your surface. So this is mainly used, for example, in the automobile industry, where you really are measuring the reflection of high gloss material. So, for example, your varnish or stuff like that, or metallized substrates, or So let's continue now. We will now be talking mainly about spectrophotometers, but now let's talk about a few of the manufacturers of measurement devices. I just have a few examples, and also from each measurement device vendor, I also just selected a few of the devices they have and they support. So, for example, X-Rite, they have the i1 Pro 2. You see it on the lower left-hand side. It's a portable device, so you can use this device to measure by hand. It measures the spectral reflection, and it's mainly used in graphics arts. Same for the i1IO table. That's basically just a holder for the i1 Pro 2 to measure in an automatic way a whole test chart. Then X-Rite has, for example, the i1 ISIS 2 that comes in two sizes, so a 4 or the XL size. It's an automatic measurement device, and it also measures the spectral reflection. Then X-Rite also has the X-Acto measurement device. You see it on the lower right-hand side. That's a portable device. It can measure densitometric or spectral reflection. And this device is mainly used in the process control, so in your printing process. But it can also be used in press and in pre-press departments. So the X-Acto is basically the predecessor of the Spectro Eye, so it replaces basically the Spectro Eye that has been around also from X-Rite. And we also have the Spectrolino and SpectroScan, but those devices are also discontinued by X-Rite. We still find them in some places, but they are discontinued, and X-Rite recommends the i1IO table as a replacement on their homepage for Spectrolino SpectroScan. Let's continue to another vendor. There's also Barbieri. Barbieri has, for example, the Spectra LFP on the lower left-hand side. It's also an automatic measuring device. It can measure the spectral reflection, but it can also do transmission measurements. So you can also measure transparent foils, for example, using this device. Yeah, because it also has a light source not inside the measurement head, but also outside, inside a table, so it can measure through the media. This measuring device is mainly used in a large format and flatbed or industrial printing, because what this measurement device also has is a changeable aperture size of the measurement head. So it can change between 3 different sizes of aperture to, for example, measure different types. So we will talk about this a bit later. Then they have also the SpectroSwing. The SpectroSwing also is able to measure the spectral reflection and also in transmission mode. And it's mainly used also in large format, but only with flexible materials. So on the Spectro LFP, you can also use thicker materials. On the SpectroSwing, which you see in the middle on the downside, you mainly measure flexible materials, for example, paper or stuff like that. And then Barbieri also has the SpectroPad on the lower right-hand side, you see it. It's a portable device, so a manual device. It measures the spectral reflection, and it's mainly used for process control in press or pre-press. So you can measure, for example, a media wedge or a press control strip. Then there's also Konica Minolta. Also, this is just these are just a few examples of the measuring devices they have. They have a lot more measuring devices. For example, on the lower left-hand side, you see the FD7 measuring device. It's a portable device. It measures densitometric and the spectral reflection. It's mainly used in graphic arts. And on the lower, in the middle, you see the FD9. That's an automatic measuring device. It measures the spectral reflection again, also mainly used in graphic arts. Nice thing about the FD9 is, as you see below, you don't have to cut out your test chart, because the measuring device also recognizes a test chart that's on a page that you put in there, even if you have other stuff around your test chart, for example, images and so on. And just as an example for a gloss measurement device, on the lower right-hand side, you have the Multigloss 268 Plus device. It's also a portable device, and yeah, it measures the specular reflection. So it's a gloss measurement device. As a last vendor, I want to talk quickly about Techcon. Techcon is a German manufacturer, and they have, for example, the SpectroDens. The SpectroDens on the lower left-hand side. It's also a portable device, but it also has rolls underneath the device, so you can also do a strip measurement using this without needing to use a ruler. And it also can measure densitometric and spectral reflection. It's used mainly on press as a process control, but can be also used in pre-press. And as an example for a microscopic image capturing device, you see on the lower right-hand side the SpectroPlate. So this device is mainly used used in the quality control of computer-to-plate systems. So here you can really measure your plate and check if, for example, your 40% has also 40% on your plate. Now let's talk a little bit about the ISO norm for color management. So there's this ISO norm 13655/2009, which describes the spectral photometric measurement of color. So first, some general information, what's inside this ISO norm. The ISO norm describes how a measuring device, what it has to be able to do. So what's inside this ISO norm? It says that a device must calibrate itself. So a measuring device must keep it safe at a stable level. So usually measuring devices have a white tile built inside the measuring device, or it's externally with the measuring device. So you place your measuring device on this white tile before you start your measurement. And then it calibrates itself. And then the ISO norm has a should and a must about the nanometers that it shall measure. So it should measure between 360 nanometers to 780 nanometers. That's our visible and also some UV light range. So, and it should measure in 10 nanometer increments. And then there's also the must. It must measure between 400 and 700 nanometers in 20 nanometer increments. And then it should interpolate also the 10 nanometer increments if it can't measure in 10 nanometer increments from the beginning. So the nanometer is the spectral range of our colors that we see. Then there's also some info about the measurement geometry. So the measurement geometry must be a 45-0 degree or 0-45 degree, which basically means that the light source should hit the surface that you want to measure in a 45-degree angle, for example, and then the sensor that catches the reflection of the light should be at a 0-degree angle, or vice versa. We will see this later also in a small image. Then there's defined when we have measured the spectral data, the spectrum of the colors, and then the measuring device has to convert those basically to, for example, LAB values. It can convert those to LAB values. And in the printing industry, we are using the D50 2-degree condition. So this condition should be used for calculation of those LAB color values. And the last thing is for the delta E calculation, for example, when you have your spectral measurement device and you compare two measured values with one another, then either the delta E formula, delta E is the difference of two colors, it should either use the delta E 1976 formula or the newer one, the delta E 2000 formula. So that's just quickly some information. Now I want to talk about the measurement geometry and about how a measurement geometry can affect the quality of your measurement. So we are now going to have a look at the 45-0 degree measurement that should be used, and below, that's an image from Konica Minolta that we are using here. Below you basically see three different possibilities how measuring devices could be built using a 45-0 degree geometry. So on the left-hand side, you have basically just one light source that's hitting the patch that you want to measure. So from one side, very directional, and then you have your sensor that's measuring. And if you would have just such a very simple light source, then of course, if you have a rougher surface that you are going to measure, it has a huge influence. If you turn your measuring device by like 45 degrees, yeah, when You see it on the second image from the left-hand side. So by doing just such a very simple 45-0-degree directional illumination, you can have a difference of up to or more, even more than 3 delta E when you measure the same patch just by turning your measuring device a little bit. So this isn't very good. In the middle, we see a 45-degree C, 0-degree, that means circumferential. So this measuring device uses, or this geometry uses a circular ring optic. So you have light coming from multiple sides, not just from one side. And when you rotate such a measuring device by 45 degrees, for example, then you can achieve a delta E difference of the same patch of lower than 1.5 delta E. So you are much better in comparison, when turning the measuring device a little bit. And on the right-hand side, we see the measuring geometry that some measuring devices use, and that's the 45-degree annular ring optic. So here the light comes from every direction, and when you measure with such a device and you turn it a little bit, you get exactly the same result measuring one patch compared to without turning it. So the one in the middle, for example, the circular, the circumferential ring optic, this is, for example, used by the i1 Pro 2. So it's quite good to use this geometry for measurement. Now let's have a look at the 45-0-degree. This is also a screenshot from Konica Minolta. So here we see what this 45-0-degree means. We have our sensor on top, which is at a 0-degree angle. Right at the bottom, we have the specimen that we are going to measure or want to measure here, and in a 45-degree angle, we have, in this case, multiple light sources that are hitting this specimen, and then the reflected light is measured by the sensor. First, it's passing a lens system, and then it's hitting the sensor, and the sensor is measuring it. And just as an example, I also want to show you a different measuring geometry that has nothing to do with 45-0-degree. So it has nothing to do that what we are using currently at the moment in the printing, in the normal printing press industry. But there's also, for example, a sphere geometry. And what is it? Here we basically have a high reflective, we have an Ulbricht sphere, that's how this light bulb is called, which has a highly reflective coating around. So it's a nice body, and the light source is a bit outside, and it shines into this body, and the light gets reflected from everywhere, and then it shines from all the sides onto the specimen on the lower hand side that we want to measure. And you see the sensor, in this case, it's at an 8-degree angle, and at the opposite angle of also 8-degree, you have a gloss trap. So here, the light isn't reflected, which means that the sensor doesn't get influenced by direct reflection of light. So it just gets the whole illumination and of the specimen without direct reflection. So it really can measure a color very nicely on a high reflective surface and also on highly structured surfaces because of the even illumination of the specimen. So such a sphere geometry is, for example, used also in the automobile industry when you measure automotive coatings and you want to measure the color there and want to get this information perfectly. So yeah, just to give you an idea about this stuff. So yeah, the ISO norm 13655, it's about spectral measurement and colorimetric computation for graphic arts images. That's what this ISO norm is about. And the current revision that we are using is from 2009. Before that, there was the ISO 13655 of revision 1996. And the problem with this old revision of the ISO norm was that the light source that shall be used inside the measurement device was not clearly defined. Which means the UV light content, the UV content in the light source wasn't clearly defined. So up until revision of 2009, we had different UV contents inside our measurement devices. And one other issue was that there was defined a UV cut, how to measure with UV cut, so without UV content in your light source. But the wavelength of the UV cut filter was also not clearly defined. So it wasn't defined if it should cut up to 420 nanometers, for example, or up to 400 nanometers or something like that. So that's why we had this revision in 2009. And the main stuff that came by this revision was we now have 4 definitions of the measurement conditions. So we now have the M0 measurement condition. That's basically the legacy mode. So in the old days, in the old revision, that was called no filter. So it was with the light bulb with UV content, but it wasn't defined. So but that was the old no filter measurement. And now we also have the new M1 measurement condition. M1 is a measurement condition that's very close to our D50 standard. So that's also very close to the standard under which we are viewing our print products. So it's very close to daylight. It's oriented highly on the daylight, and the M1 measurement condition now also has a defined amount of UV content that shall be in the light source, very close to what we have outside in the daylight and inside our viewing booths that we are using. So that's very good. So all the new standards that are coming out, for example, FOGRA 51, FOGRA 52, also the newer US standards, they are based on M1 measurement data with the defined UV content to be much closer to what we actually see under the new norm light. Then in this norm, there's also M2 measurement condition defined. So M2 means UV cut, but now with the revision 2009, the wavelength of the UV cut field is also clearly defined. And then there's also the M3 measuring condition that's basically with a polarization filter and also UV cut. Now, what influence does it have when we have inside our measurement device, if we have UV light in the light bulb that's hitting the surface that we are measuring? So basically it only has influence if the media you are measuring has optical brightening agents inside. So let me jump to the next slide and let me explain it a little bit. When your media or your inks that you are using contain optical brightening agents, OBAs it's called shortly, that means that OBAs turn invisible UV light, to our eye invisible UV light, into visible bluish appearing light that's reflected from the surface. So that's what OBAs are about. And here we measure basically a media, a paper that contains optical brightening agents, and we measured it with M0, M1, and M2. So the green line in the middle is the measurement with M0. So we used a measuring device with undefined UV content in the light source. And you see that in the nanometer range of like 400 to, in this case, 520 nanometers, we have optical brighteners that are then reacting to this UV light and returning a bluish appearance. If we have a look at the M1 measurement, so the measurement using a defined UV light very close to daylight, then we see here a higher reaction of those optical brightening agents, and we get a higher amount of bluish light when we measure it here using the new M1 condition. And M2 is the UV cut condition, so no UV light in our light bulb that's hitting the paper. So here we see that nothing reacts, nothing gets excited, the OBAs don't get excited, and so yeah, they are not measured then. The OBAs are not measured then. So the bluish light here is mainly between 420 and 470 nanometers. If we have a look at this example also in a different view, then here we have the AB graph. The AB graph is how we recognize colors, basically. So on the x-axis, you see basically on the left-hand side it's a bit greenish. On the right-hand side it should be a bit more reddish, and on the y-axis, you see the further it goes down, it means it gets more bluish, and the further it goes up, it means it gets more yellowish. So when we measured the probe using the M2 measurement condition, that's the one on top in blue, we have a very neutral, slightly greenish result when using this condition when we measure an OBA containing paper. Then in green you see the result using the M0 measuring device. So here optical brighteners get excited and turn the measurement result into a more bluish result. So we have a B value of -4, and it also gets a bit more reddish. And then using the M1 measurement condition in red, the one on the low-hand side, we see that, yeah, even more OBAs, they react even more because there's more UV light in the light source, so it gets even more bluish and a slight hint more reddish. And if we would look at this OBA containing paper under the new norm light, under the current norm light, then it would also reflect to our eye, we would see, as we measure here with the M1 measurement condition, so with 100% UV light. Now, what influence does this new M1 measurement condition have on our daily working practice? It's relevant mainly for substrates that contain optical brightening agents. So if you have substrates or inks that have OBAs inside, and then the M1 measurement condition and also the viewing then on the new norm light will have a nice match, a nice result. So we measure now what we actually see under this norm light. If you have substrates without optical brightening agents, then it really doesn't matter if you measure M0, M1, or M2, because then the result will be very close to one another. So the resulting measured LAB values will be very close. Now let's talk about measurement devices that are supporting currently M1, the M1 condition. So for example, the X-Rite i1 Pro 2 supports this measurement condition. Also the X-Rite Exact, the ISIS 2, and then the Epson ILS 30, the Canon SU21. From Barbieri, the SpectroPad is supporting this condition. From Techcon, the SpectroDens. Yeah, and from Konica Minolta, the FD7 and FD9 all support this measurement condition. when we are talking about measuring M1, there's also differences in how measurement devices handle this. The Konica Minolta FT7, FT9, also the X-Rite Exact, and the Techcon SpectroDens, they are measuring basically real D50. So they have a real D50 light source, which means those measuring devices have multiple LEDs inside, and by driving those LEDs in a certain way, you have in one measurement the UV light content that you need, and also the D50 curve that you need for measuring the color. So using these devices, you just have to go over your strip or over your patch once, and in this one measurement, it gets all the information, UV and normal information. There are also other devices, for example, the i1 Pro 2 or the iSys 2, and they have to measure twice over each row or twice over each patch, because in the first pass, they are measuring only UV cut, so without UV content in the light source. And then in the second pass, when you measure again the same strip, then they are measuring only UV content, as an example. Yeah? And then the M1 result is being calculated from those two measurements. So yeah, those are the two differences that are existing in measurement device technology. Now let's talk about some frequently asked questions. So customers ask us quite often if they have to buy new measurement devices, and what we tell them is basically if you are handling M1 references, and if you are handling brightened substrates or inks, then yes, we definitely recommend you to use a new measurement device. So for example, if you want to prove the new FOCRA standards 51 and 52, and you then want to measure the media wedge that's on your proof, because the references of FOCRA 51 and 52 are made only in M1, and you also need an M1 measurement device to be able to measure your control strip. So in such a case, yeah, you would need a new M1 capable measurement device. Then, yeah, do I have to create new profiles with M1? Also here we say yes, if your reference prints are affected by OBAs. So if you have, again, OBA containing substrates and inks, and you want to create own reference prints and own reference files, then yeah, we recommend to use M1 technology to really get all the information that's inside your media also reflected in your reference measurements. And then M1 should be used for creating the characterization data, so the target value is for profile creation on your proofing device, for example, and also for verification, for example, of the media wedges, if you want to create a proof. Now let's talk about how much can we rely on our measuring devices. When we are talking about reliability of measuring devices, there are basically three types that we can talk about. So we have first the repeatability. So the repeatability describes when you have the same measuring device and you measure the same patch over and over again, how close, how comparable are then those measurements that you're taking with the same measuring device of the same sample? Yeah, how comparable are they to one another? So how good is your measuring device? How stable is it from measurement to measurement? Then we can talk about the inter-instrument agreement. So the inter-instrument agreement describes basically the difference of measurements between a master device that, for example, a measurement vendor has in his the master device they are using basically, and then all the measurement devices that they ship outside. So how close is it to their master device? And then there's also the intermodal agreement that we can talk about. The intermodal agreement defines basically the difference of measurements between devices of, for example, different manufacturers or of different design or different model. We will talk about a few of those now in the next slides. So what's the theory about repeatability and inter-instrument agreement? So Andy Williams from the IFRA. The IFRA is the World Association of Newspaper and News Publishers. He wrote, the inter-instrument agreement is usually indicated by a color difference value between two instruments or between a master instrument and the average of a group of production instruments. Although various ways are used to describe this color difference, a common value is the average or mean value for a series of 12 British Ceramic Research Association Ceramic Color Standard Series 2 ceramic tiles. A value of 0.3 delta E is acceptable. So and there's those ceramic tiles from the BCRA, and those are mainly used at manufacturers of measurement devices, and they measure those tiles, and then they publish. When they bring out their measurement device, they publish this information in the specs. We will have a look later at one of the specs of a measurement device, and how good is their inter-instrument agreement, and how good is their measurement device compared to their master measurement device. What does it mean in practice? Don't expect that two spectrophotometers agree within 0.3 delta E's. And also what's seen, an average agreement of 1 delta E is not uncommon in practice. It could be even more between two measurement devices, because of course measurement devices in the wild, I would say, they could be even higher depending on the humidity. They are placed on the temperature, on state of the last certification or calibration, and so on. So there can be a difference. Let's just have a quick look about just a specification of one measurement device. So you see that all what we are talking here is also then can be seen in the specification of measurement device vendors. So this is also an example I got from the Konica Minolta homepage concerning the FD9 measurement device. So here we see on top that this measurement device was built with the 45-degree annular illumination. On a few slides before, we've seen the annular illumination. That's where the whole, where we have a very nice illumination of everything, basically. If we go a bit further down, then we also see the wavelengths that this measurement device can measure. So this measuring device can measure between 380 and 730 nanometers, and the wavelength pitch is 10 nanometers. We also see here that the measurement area is 3 millimeter. So 3 millimeter is the patch size or the area of measurement that is going to be measured. There are also other measuring devices that, for example, use 2 millimeters or 6 millimeters or even 8 millimeters. And for example, a 3 millimeter size is perfect for our printing conditions. If you have a larger patch size that you want to measure, for example, 6 millimeter, that could be useful maybe when you measure a UV printing device, where you have a bit more structure. Then this might be helpful, or an 8 millimeter aperture is, for example, used in textile measurement. So where you have the structure of your textile, and then a larger aperture helps usually to flatten the results to get it more even measurement results. Then we see here that the light source inside this measurement device is LED, so it's based on LED. Some other measurement devices are using light bulbs, but the LED technology is state of the art. Then what's also described here, yeah, and the short-term repeatability is basically what I said before. It's the where you measure one sample using the same measurement device over and over again. So with this device, you have a repeatability within delta E of 0.05, so very good repeatability, also because of the angular illumination and other factors. And then here's also some information about the inter-instrument agreement. So Konica Minolta measured the BCRA tiles, the ceramic tiles, and compared those measurements to their master body, and they reached the value of delta E 2000 within 0.3 delta E. Yeah, so here we really get some information on the lower hand side. The second from the end, it's the measurement conditions. Here we also see what type of light can this measuring device use to measure the colors. So this measuring device can use M0, M1, M2, which we talked about earlier, but it can also measure in a lot of other different lighting conditions, even user-defined lighting conditions, because it uses the LED technology, and with the LED technology you have multiple LEDs, sometimes 7 or something like that, inside your head, and by using a different driver to drive the LEDs differently, you really can get a huge range of lighting conditions inside your measurement device. Now let's go into tips and tricks session. So how to handle your hardware. First, some general rules about handling your measurement devices. The measurement device vendors really recommend to recertify your measurement instrument at scheduled times to maintain the measurement accuracy and optimum performance. So this should be done. Recertification is usually by sending your measurement device in, and then it gets recertified. Then what's very important, that measurement devices should be kept clean. So that means the instrument, the calibration plate, so the white tile, for example, and also the backing material. And yeah, assure that you use the correct calibration white tile for your measurement device. For example, if you have two measurement devices, for example, two i1 Pros, then you shouldn't switch the white tiles, because the white tiles are really, your measurement device is really calibrated to a specific white tile. So this should be kept in mind, not to switch them. Usually they have a serial number on the backhand side, and also the serial number is on your measurement device, so you know that you have the correct white tile for your measuring device. And we also recommend to use a stable backing material when you are measuring samples. So this is especially for external measurement devices. So we recommend, or we usually use at GMG 2 to 3 sheets of our proofing paper, the Cinema 250 proofing paper, as a backing, for example, on the i1IO table, or when we just do a hand measurement with the i1 Pro 2, we usually use this as a backing to have a stable backing. And now let's talk about some tips and tricks for specific measurement devices. The i1 Pro and the i1 Pro 2. Here, when you want to measure a row, then we definitely recommend to use the ruler for your measurement. Don't just take the measurement and try to do it by hand. using the ruler really helps to get better results in measurement. Then yeah, you have to find the right speed for the measurement, so get the right feeling for the instrument. The contrast between the patches has to be high enough. So for example, if you get a print on a very yellowish or brownish paper, then the contrast between patches sometimes isn't high enough. So the measurement device, when just doing a strip measurement, it doesn't recognize the differences in between. So you would have to switch to a patch measurement. And yeah, patch measurement with a hand measurement device is usually not the best idea. So in this case, we recommend to use, for example, the I1IO table or another measurement device to do this. And when you are measuring, it usually helps to apply a bit of pressure on the measurement device head, just to get a correct measurement, to not get some stray light inside your measurement when measuring. Now some tips and tricks for the I1IO table. The I1IO table can be changed depending on your media height. So for example, if you're printing on a corrugated board, a thicker corrugated board, you should set the media height of your I1IO device a bit higher, depending on the thickness of the media. You should place your test chart, of course, in the measurable area of the I1IO table. What the I1IO table is doing also when driven with our software is if a strip measurement fails, then the measuring device automatically switches to patch mode. Then it measures this failed row in patch mode, and after that it switches back to strip mode and tries to measure the next row again in strip mode. So it's quite intelligent when measuring. One thing to keep in mind when using the I1IO and I1IO2 is, for example, when you are measuring in M0 mode, then it's possible to use 7mm patches. So a patch size of 7mm is enough. When you are using the I1IO table for M1 or M2 measurements, then bigger patches are needed in order to do the scan mode measurement. That's just defined by X-Rite and defined by the driver to drive the measurement device, because in M1 and M2 the measurement device has to drive twice over each strip, and it tries to do that on two different areas of the patch, and that means the patch must be larger than 7mm. So just keep that in mind. If you want to measure M1 with 7mm patches, just switch to patch mode. It will take a bit longer, but it results also in the measurement you want. Now some tips and tricks for the I1 ISIS and I1 ISIS 2. These devices come in two sizes. So there's this device in the A4 and XL size. So you should use the correct measurement chart size for whether you're using the one or the other device. You should insert the measurement chart when the blue light lights on the ISIS, not before, because it first does some initializing before you can insert your test chart. And the test chart should be cut off properly, so especially the left edge should be cut properly in order for the measuring device to being able to measure it correctly. The bars are needed, so the black bar on top, and it needs to have a high enough contrast, so the measuring device recognizes it and knows that after that the patches are starting. And when you are measuring using the ISIS or ISIS 2, and you are measuring in M2 measurement mode, which means UV cut mode, it measures every row only once. If you are measuring with M0 mode, or that's for the ISIS 1, or for the ISIS 2 it also can measure in M1 mode. Then it measures every row twice, so it takes a bit longer to measure a test chart, but yeah, that's it. So that's the tips and tricks here. And now some last, some tips and tricks for the exact measuring device. The exact measuring device is basically the predecessor of the Spectro I measuring device. So this measuring device, in this measuring device, it has a touch panel, and you can also use it to compare directly inside your measurement device two measurements of two samples that you are measuring. So if you open the menu and you go to basic compare, then you can go to standard, and then you measure your reference measurement. And after that, you can measure all your other samples, and then they are compared to your standard or reference measurement. The exact measurement device also has integrated spot color libraries. So the Pantone libraries are inside the measurement device, and it has a best match functionality. So if you get a sample from a customer, you can just measure the sample, and then the measuring device recommends to you the best matching Pantone spot color to reproduce this color. And this measurement device can also measure in M1 mode or M0 or M2. And when you are switching to M1 or away from M1, then you have to recalibrate the measuring device, because this measuring device also uses the LED technology. So when you are switching to M1, the driver that's driving the LEDs changes the lighting condition, and after that you just have to do a quick recalibration, and then you can measure in M1. And if you switch back to M0 or M2, you also do again the recalibration. Some tips and tricks concerning the Barbieri Spectro LFP. Also, with this measuring device, you should cut out the test charts accurately. The bars on the left hand and on the top side, the black bars, are also needed, because the measurement device then finds automatically those bars, and then it knows where the patches that it shall measure are basically lying. And then, if this positioning fails, just check where it failed and reposition your test chart and try again. The measuring device, as I said before, has different apertures. So it has aperture size of 2, 6, or 8 millimeter that it can switch automatically. And which aperture is used is basically defined by the patch size of your test chart. Then Barbieri also has a gateway software, so it's their own measurement software, and you can use this measurement software also for analysis of the measurement device. So if it makes some problems, you can use the software and check if all the mechanics are working. And the measuring device also can do a transmission measurement. When doing transmission measurement, then the measurement device first calibrates itself, so it shines through a white part of your test chart page and calibrates itself. For example, if you have a more milky, milky appearing paper or transparent foil, then it needs to measure every patch longer to get enough light into the head. And if you have a more transparent material, it measures shorter to get all the light it needs into the head. So just keep that in mind. And then there's also the Barbieri Spectro Swing. That device uses the same test charts as the Barbieri Spectro LFP. And it's also an XY measurement device. Now we are going to talk about the XRGA standard from X-Rite. I'm seeing it's now 5 o'clock, so we will need a bit more time, so around 15 minutes. It will take around 15 minutes to close this session. The XRGA standard is a standard X-Rite defined, because X-Rite when X-Rite merged with Gretac Macbeth, they had the issue that X-Rite had a nice standard for their measuring devices, so X-Rite devices were comparable to one another, and also Gretac Macbeth, before the merge, had their own standard calibration, and all their measuring devices also were comparable to one another. But now with the merge, there was a slight difference between the calibration of the X-Rite devices and the calibration of the Gretac Macbeth devices, which meant that X-Rite wanted to make the measurements from the one series of devices and the other series of devices comparable to one another. So that's why they wanted to make the inter-model agreement that we talked about earlier. They wanted to make this better. So then they worked on their own XRGA standard, the X-Rite standard for graphic arts. And this standard defines that a measurement from one device needs to be converted spectrally and on LAV basis in order to match the XRGA standard, and other devices are also converted to this XRGA standard. In the beginning, they did this by software and software drivers, or we had implementations into our software. And new devices like the i1 Pro 2 or the ISIS 2, they produce native XRGA measurement data. So here's just a quick graph how this looked, for example. So here we see the color shift that happened basically to, on the right hand side we write from GMDI to XRGA. So this color shift is showing how Gretac Macbeth measurements of colors had to be changed in order to be in this XRGA standard. So we see here on the lower side, we see the cyan area, and cyan, the cyan area tends to get more bluish and more reddish. So it turns to the down right-hand sides. The red area on the right-hand side gets more yellowish, and the green areas on the left-hand side, they turn also more bluish and also a bit more reddish. So it's like a slight turn of the whole area of measurement to convert GMDI standard to the XRGA standard. And this is just informational, because usually you don't have to work with such stuff, because this is done by software automatically. So for example, handling XRGA in GMG software, our software basically uses XRGA tags to convert data automatically. So for example, when you measure with our software and you export the measurement data, then it's automatically tagged whether you used an XRGA measuring device or non-XRGA device. And then all of our software is working with this. And we are the only software vendor capable of converting XRGA backwards to GMDI for correct proof verification. Which, what does it mean? Basically, FOCRA 39, for example, the FOCRA 39 standard was created using the GMDI standard. So the LAB measurements are inside this GMDI standard. If you now print a measurement, a control strip on your proof, a media wedge on your proof, and you verify this media wedge using an XRGA measuring device, then you are basically comparing XRGA to GMDI, which might give a problem. So what we are doing directly in the background, we are converting the XRGA back to GMDI, and then we can compare it correctly to the GMDI data of FOCRA 39. And yeah, then we really get a perfect validation of proofs. And yeah, I mean, this sounds now very complicated, and it is, but it's handled by our software completely automatic, and you don't even need to worry about this stuff. Yeah, because here we see in our proof control software, proof control is used to measure media wedges on proofs. We also tagged all the standards that are in there depending on where the original reference data came from. So for example, we have standards that are in XRGA on the lower right side. This is tagged as XRGA, and Focora 39, for example, would be tagged as GNDI. XRGA and GMG software, so currently supported measurement devices. I hope this is a complete list. I'm not 100% sure. Is the X-Rite i1 Pro 2, the X-Rite Isis 2, with new drivers, also the old i1 Pro, the i1IO table, the X-Rite i1 Isis, the X-Rite Spectralino SpectroScan, DTP70 SpectroProver from Epson, the ELS20 and 30, and the internal measuring device of the Canon printers, the SU21. All those deliver XRGA data, and this data is also used in our software. When we are talking about software for measurements, most vendors of measuring devices also have their own software to use to measure using their device. So for example, X-Rite has the i1 Profiler, which supports X-Rite devices. So for example, the i1 Pro, i1 Pro 2, i1IO and 2 table, the i1 Isis and i1 Isis 2. Then X-Rite also has a discontinued product. It's the measure tool. It's discontinued now, so the i1 Profile is the predecessor, but the measure tool could also be used. It was part of the measure of the profile maker from X-Rite. Barbieri, for example, also have their own software, the Barbieri Gateway, which you can use, and there are many more. And then, of course, there's a measurement software from independent software vendors. Here just two examples for software by us, by GMG. It's the GMG Profile Editor, which can measure and export LAB values from measuring devices. And we have, for example, OpenColor, which is able to measure spectral data and also export spectral data, work with it. Now the last foil, basically. When you're considering buying a measurement device, when you're choosing a new measurement device, then there are a few things that you need to consider. So first, you have to consider which is the area of application of the measuring device. So do you want to use it for quality control in press, or for printing plate measurement, or for profile creation in pre-press? So what's the main intent of this measuring device? And then you have to consider if you need the M1 measurement condition. So if OBA media, so media that contains optical brightening agents or inks that have OBAs, then definitely it's recommended. And yeah, most of the new measuring devices that will come out also support M1. So this is definitely the future of measurement. Then you have to decide, do you need an automatic measurement device, or is a manual measurement device enough for you? So do you need to measure larger test charts, or is it okay to just measure some sample patches? And then you also have to take into account and check if your measurement software or your product, your measurement software product that you are using, is the measuring device also supported in there, or what measuring devices does the software support? So I showed here in this presentation also some measuring devices that aren't yet or aren't supported by our software. And last, if you already have some other measuring devices in your company, and you're buying a new one, does it need to measure exactly the same as the other one? So do you need absolute comparability? Or could it be from a different vendor, which is also quite close, but might be a little bit of different. So also this should be taken into account. Now, yeah, we are final here with our presentation. And if you now have questions, you can ask those using the chat function. I will just wait a minute or so, or half a minute, if any questions appear. Okay, no more questions. Then, yeah, if you need further information, you can also visit our homepage at gmgcolor.com, Know-How Academy. We can also have a look at other stuff we are showing. We also have detailed trainings on site or in our academy, in our head office. So yeah, just have a look at this, and thank you very much for your attention, and yeah, have a nice day. Thank you.